Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll implement optimization component of linear regression model from scratch. There are two ways to implement the optimization component. The first one is with the method of normal equation and the second one is through the gradient descent procedure. The normal equation method sets the partial derivative of the loss function with respect to weight vector to 0 and then solves the resulting equation to obtain the weight vector. Whereas gradient descent method iteratively adjusts the weight vector based on the learning rate and the gradient of loss function at the current weight vector. In order to implement these components, we'll need basic Python libraries like NumPy. We'll also need some of the useful functions that we implemented in previous collabs. Specifically, we'll need function to generate synthetic data, then pre-processing of the data like including dummy feature and training test split, then the function for model inference and loss calculation. Let's generate training data with 100 examples and we'll use linear regression model with known parameters to generate this data. We'll use this data to test optimization procedures where we compare the estimated weight vector with the actual weight vector. We generate the data and we pre-process it to obtain the train test split. So we have training feature matrix, test feature matrix, training label vector and the test label vector with us. First, we'll use normal equation method to estimate the weight vector of the linear regression model. And the implementation is fairly straightforward in a vectorized form. We make use of np.linalg.pinv for calculating pseudo-inverse of the feature matrix. The weight vector is obtained by taking the pseudo matrix of the feature matrix and multiplying it with the actual label vector. To test this function, what we'll do is we'll use the data set with known parameters or with known weight vector. So we have already generated a synthetic data set with known weight vector. We'll use that data for testing whether the normal equation method or normal equation implementation works as per our expectation. In the test, we set up the feature matrix and label vector from the synthetic data and we also set the expected weight vector. We set it to the value of the weight vector that we use to generate the synthetic data. Then we call the normal equation method on the feature matrix and the label vector to obtain the estimated weight vector. Then we check the shape of the estimated weight vector, whether it has got two numbers in it, and finally we check whether the content of the estimated weight vector is almost equal to the expected weight vector. And you see that the test passes. So the normal equation function works well for the given setup. Next, we'll implement the gradient descent procedure. Gradient descent procedure randomly initializes the weight vector to 0 and then it has a loop until convergence. In the loop, it first calculates the partial derivative of the loss with respect to the weight vector. Then it calculates new value of the weights and finally update the weights to the new value simultaneously. In this implementation, we use number of epochs as a convergence criteria. So there are two important steps. One is calculation of the partial derivative of loss function with respect to the weight vector and second is calculating the weight updates to obtain the new values of the weights. So let us implement these two steps into separate functions and test them individually before implementing the gradient descent procedure in general. The partial derivative of the loss function is obtained with the following formula. It is the multiplication of transpose of the feature matrix with the difference of predicted and actual label vectors. Again, the vectorized implementation is pretty straightforward. We take the transpose of the feature matrix and then multiply it with the difference of the predicted and the actual label vectors. We test this implementation with a feature matrix with 2 examples and 4 features. Then the weight matrix, since we have 4 features, weight matrix will have 4 entries, and since there are 2 examples, we'll have 2 entries in the label vector. Then we substitute the values for each of these quantities and perform algebraic manipulation. After performing simple matrix vector multiplication and algebraic manipulation, we obtain the gradient vector containing 15, 105, 50 and 95. So this is the gradient vector or the partial derivative of the loss with respect to the weight vector. Let us test the implementation of the partial derivative with this particular setup. So we set up the test case with the feature matrix, weight vector and label vector from our example, and we put the value of the expected gradient as we obtain after performing the mathematical operation. Then we calculate the gradient calculation method and store its result into the grad variable. Then we make sure that the grad variable has 4 entries in it, and we also check that its content are almost equal to the expected gradient. And you can see that this test also passes. Next, we'll implement the weight update part. In order to obtain the new weights from the old ones, we basically subtract the old value. We basically use the old value and subtract the gradient weighted by the learning rate. So W new, which is the new value of the weight vector, is set to the old value of the weight vector minus learning rate times the gradient vector. So that is how we get the new weight update. So again, the implementation is quite straightforward. It's a one-line code where we take the value of the old weight vector and subtract learning rate times the gradient vector. Let us work out an example for the weight vector update. So we have, let's start with a weight vector containing 4 entries or with the shape 4, 1 with all ones, and we have a gradient vector again which has got 4 entries with 15, 105, 50 and 95. With learning rate of 0.001, let's calculate the weight updates. So the new value of the weight is equal to the old value of the weight minus learning rate times the gradient. So alpha is the learning rate here. So we substitute the values of respective quantities and perform algebraic manipulation, and we obtain the new weight vector which you can find over here. We use this hand calculation for setting up the test for the update weights function. We have the weight vector containing all ones. We have a gradient vector containing 15, 105, 50 and 95, learning rate of 0.001, and then we have the expected new value of the weight vector as we obtain by solving for these quantities. We call the update weights function, get the value of the new weight vector, and we make sure that it has got the shape of 4 and its content are almost equal to the expected new weight vector. The test passes for the given setup. Now that we have these building blocks in place, let us implement gradient descent procedure. So you can see that this is the step where we are initializing the weight vector to 0, 0. Then this is the step where we are calculating the partial derivative, and this is where we are updating the weight vectors. And other lines are mainly for bookkeeping. We store all parameters or all weight vectors across all the iterations as well as errors across all the iterations. And we calculate the error by using the weight vector in that particular iteration. So we use the loss function for calculating the error in a particular iteration and store it in the error underscore all variable. We also store the weight vector for the corresponding iteration in w underscore all variable. And finally, we return the final weight vector, all errors across all iterations and all weight vectors across all iterations. So errors across all iterations is useful for plotting the learning curves, and all weight vectors help us in checking out the trajectory of the gradient descent procedure. Let's first test this function with the synthetic data that was generated earlier, and we know the actual weights for that synthetic data, so we can check whether the gradient descent procedure also results into similar weights. So we set up the gradient descent procedure with the feature matrix and label vector from the synthetic data, and we know that the synthetic data was generated with weight vector of 4 and 3. We call the gradient descent procedure with learning rate of 0.001 and with number of epochs to be 2000. We make sure that the weight vector has 2 entries in it and its content are almost equal to the expected weight vector. And you can see the run of the gradient descent procedure in the log here. So we have set the gradient descent procedure for 2000 epochs, and you can see that the loss is going down after each step, which is a good sign, because as we make more and more iterations of gradient descent, the loss is expected to go down, and that is what is happening, and this is as per our expectations. Let's try to plot the trajectory of the gradient descent procedure. We'll use the weight vectors stored across all the steps for this particular process. So you can see that the red dotted line here is the initial model that we obtained with weight vector of 0, 0. And then as we did more iterations of gradient descent, we get a new weight vector and we plot the corresponding model, which is a line in this particular case. So this is a line that we have after the first iteration, after second iteration, and so on. So you can see that as we make more and more iteration, we finally have lines that is closely matching, or which is closely modeling the given data set. We can do such a visualization because currently we are operating on a problem with a single feature. As we solve more real life problems which normally have a lot of features, such an approach will not work. So as we said, learning curves are our best friends in that case. So what we'll do is we'll plot the learning curves, and we'll plot the learning curve for one gradient descent run. So you can see that this gradient descent run has learning rate of 0.001, and we run it for 2000 epochs, and learning curve has number of the iteration ID on x-axis and the loss on their y-axis. So you can see that initially the loss was very high, 16,736. So it's very high, and after that it It suddenly dropped to 129 and then it went on gradually decreasing. So one of the tricky question, or rather there are two tricky questions in setting up gradient descent procedure. One is how to decide the learning rate, and second is how do you set up the number of iterations to a large enough quantity so that gradient descent has enough time to reach the minima. So you first check, the convergence characteristics of the gradient descent algorithm with different learning rates. So we try the values of the learning rate to be 1, 10 e to the power minus 6, minus 4 and minus 1, and we run gradient descent algorithm for 2000 epochs each, and then we compare the convergence characteristics of these different runs. So you can see that when we had a very small learning rate, which is the first quantity over here, you can see that the drop in the training loss was gradual. It was not sudden, all of a sudden, right? So we went from 16,000 to 9,000 to 5,000 to 3,000 and so on. So you can see that we have a smooth learning curve which is going down gradually. Let's try another learning rate which is higher than the current learning rate, order of magnitude higher than the current learning rate. And you can see that for this particular learning rate, which is 1 e to the power minus 4, this learning rate, there is a reduction in the loss is quite drastic, right? We started with 16,000, we suddenly dropped to 129, then 200, and then there is a gradual loss, a gradual decrease in the loss. And you can see that compared to the earlier learning curve, this learning curve is pretty sharp, right? So let's try even higher learning rate, let's say 0.1. And you can see that, for the zero initialization, we had 16,000, loss of 16,000. After that, we have infinite number and then an n. So what is really happening here? If you ever see such a characteristics in your training run, then you know that there is some problem. I mean, you are using probably a very high learning rate, because of which model is not making any progress. Rather, it is diverging. It is not going to converge to the local minima. So when such a thing happens, you should stop the training run, reduce the learning rate, and run it again. Finally, I leave you with a couple of exercises. One is to study the effect of number of steps or iterations on convergence of gradient descent. Here we studied the effect of learning rate on the convergence. I would like you to study the effect of number of steps on the convergence. So choose the learning rate of 0.00001 and use the synthetic data that we have used in this collab. And for this learning rate, you should vary the number of steps from 10 to 10,000 in multiples of 10 and study the convergence for each number of steps and write down your observations. Second exercise is we use a simple criteria for convergence in terms of number of epochs, but we know that this criteria may not be optimal, because if we have that criteria, then no matter what, we keep running the loop till we exhaust the number of epochs that we set initially. So other way to stop gradient descent procedure is by checking if weight vector changes. If there is no change in the weight vector, we can terminate the gradient descent procedure, and that turns out to be one of the more efficient approach, right? I mean, you should have enough number of iterations as well as this particular stopping criteria, so both of them make gradient descent procedure more efficient. So I would urge you to implement this weight convergence criteria to stop the gradient descent procedure. In the next video, we'll learn variations of gradient descent algorithm and their implementation.